All right, welcome back. By the time you guys are watching this, I think you guys will probably be a little knee-deep into doing the exam. But anyway, we're almost at the end of chapter 19, so we've been spending, I believe this is going to be the third lecture that we're going through just one chapter. So let me just pause and make a salient point in that, if we're spending 3 lectures going through one chapter, there's a lot of information in that chapter, right? So now, I know you guys already know this, and I'm not telling you, I don't think anybody's like, oh, geez, really, it's important, right? Okay, but all I'm saying is that there's a lot of information in this chapter. It's pretty dense. There's a lot of reactions. Please make sure you're spending the appropriate time with it. Carbonyls and all the other chapters we're going to go through with carbonyls. The real challenge with them is not necessarily the mechanisms, right? We've been talking about those, and I think at this point, hopefully, if you guys have been following along and working your practice problems and the in-chapter problems, you've seen they all work the same way. Negative attacks at the carbonyl, positive attacks at the oxygen, right? So the mechanism isn't the challenging point. The challenging point is taking all these tools that we have, how to make carbonyls, how to reduce them, how to add things, how to transform them, and stringing them all together into coherent, logical, elegant, synthetic projects, I guess, right? The multi-step synthesis stuff that the book starts to focus on more and more and more as we go through, right? So just keeping all those things straight and in line is going to be the challenge that we have, okay? So anyway, today we've got just another set of reactions to deal with. And really these reactions deal with 2 things, either adding hydrogen to carbonyls or adding carbons to carbonyls, okay? So those are the 2 broad topics that we need to talk about. Now, adding hydrogens to carbonyls, really easy. We're only going to learn about 2 reactions, although these are reactions that you guys already know because you learned them back in chapter 12, okay? But that's fine. Let's do a little bit of review here. Today's a purple kind of day, I guess. All right. So let's say we have Mr. Carbonyl, right? And I put that in the presence of LAH. Now at this point, you guys should recognize what LAH is: lithium aluminum hydride. It is one of the most powerful reducing agents that we have. What does it mean to be a reducing agent? That means it adds bonds to hydrogen, it removes bonds to oxygen, right? That's kind of the simplified organic view on things here, right? It's always around in an excess. We can't really control it. It's kind of the nuclear bomb of reduction, right? It just reduces everything, right? It'll reduce ketones, it'll reduce aldehydes, it'll reduce esters. If we punch it really hard, we can get it to reduce carboxylic acids, and we can reduce other functional groups, cyano groups react with, right? It goes after everything. It's not very selective, okay? That's the point that I want to say with it. But anyway, if we do this, right, what we end up with is the alcohol there, right? It's not going to be selective. That's a racemic mixture, right? We can make the R and the S isomer, or the R and the S enantiomer, I should say. And but who cares at this point, right? So LAH reduces aldehydes, reduces ketones. If you have a ketone, it's going to reduce it into a secondary alcohol. If you have an aldehyde, it makes it primary. Now we've got to pause and think real quick though, okay? LAH is a powerful base, right? It's a really powerful base. So remember, whenever you're using LAH, you always got to come back in and make sure that you're doing some kind of aqueous or acidic workup at the end, right? Because technically speaking, that H right there, that one in green, is coming from the water or the acid workup that comes afterwards, okay? So don't forget to clean up stuff once you're done with it, right? If you're under basic conditions, we typically always have to come back and reprotonate any amphoteric hydrogens that might have been around, okay? So there it is. Well, not amphoteric, acidic, sorry. Alcohols are amphoteric. But anyway, so we've got that there, right? Great. We discussed a more selective set of reactions, or reagents, I should say. I don't know, man. Let's draw that a little bit nicer. It's kind of a, let's say, a friend to LAH. That's sodium borohydride, NaBH4, right? So a milder hydride source. It doesn't have the aluminum with it. The aluminum actually does quite a bit in the reaction for LAH there. Aluminum and oxygen are very, very good friends, and it kind of helps things proceed along. Boron, right, is right above aluminum on the periodic table, very similar reactivity and all these kind of things, although it does have very different properties that we can kind of use to modulate the reactivity, right? So sodium borohydride, a milder reducing agent, selective towards aldehydes and ketones, right? So don't forget about those, and we're going to come back to these a little bit later as we look at derivatives of carboxylic acids and carbonyl groups, right? But these are the two things that we learned. We kind of end up at the same place here. Typically with sodium borohydride, you would need to come back with some kind of workup also. Although I see it written in a couple different ways. Sometimes they just put in the correct solvent in here that already adds the proton and all this kind of stuff. I'm fine with that, right? You know, just for simplicity's sake and just for consistency's sake, right? I just go ahead and add a water workup to these anyway. It's not going to hurt anything. It's not going to be wrong, you know. So, but whichever way is fine. Like I said, there's a million ways to run reactions. We just have to make sure we stay within the bounds of the correct reactivity, right? Fantastic. So that's it. Effectively, what do we do in these cases? We're adding a hydrogen to the original carbonyl carbon, right, in both of these cases, and we reduce our aldehydes and our ketones. Fine. This is all review. There's not too much to really say here, right? Excuse me. The next big chunk of ideas that we have to talk about, and perhaps I'll go ahead and say it, the more useful, the more important, is not necessarily that we can reduce things, is that we can take our carbonyls and make larger carbon chains with them, okay? Again, we go back to our previous idea that we've already discussed, and that's the idea of Grignards and organolithiums. As I hit my toe, that feels good. All right, so if I bring in a Grignard, okay, and every time you have a Grignard, you're basically going to have a water workup or an aqueous acid workup also. Remember, what do you see when you see a Grignard or organolithium? Really, all you have is a carbon with a lone pair and a negative charge. That's all it is. Okay. Do you remember how to make a Grignard? Right. Some Grignards you can buy in a bottle, and in fact, actually quite a few of them you can. Right. But if we want to make a Grignard, right, we have to first make the alkyl halide, and then we have to generate the Grignard by addition of the magnesium and maybe even a little bit of a catalyst in there. Usually iodine kind of helps out with that, right? If you guys were fortunate enough to actually run stuff in the lab, then typically you guys would have made a Grignard, and it's a very common reaction to run in an undergraduate organic lab, right? And honestly, kind of fun because it is something practical, right? Grignard's very, very important. Anyway, when you see a Grignard, lone pair, negative charge on that carbon, powerful base, not really a good nucleophile, right? It's way too strong a base to be considered a good nucleophile, although on paper, I guess we could call it a good nucleophile because it does have a negative charge and it wants to go after positive things. Although Grignards by far will react more nucleophilic will react more basic than nucleophilic, okay? So if we have a powerful base and we are and we have a carbonyl around, right, then we already know what's going to happen. This is just equivalent to a carbon with a lone pair and a negative charge, right? That's all it really is equivalent to. So we will just use that. We attack at the carbonyl carbon, we kick that up. Let me zoom out here, give myself some space. There's this, that, and we bring in that ethyl group right there, and then we just finish things up with the aqueous workup or the acidic workup, and then we have our final product. Okay. OH, done. Okay. Nothing shocking about this. Something negative attacks at the carbonyl carbon. Oh my, right? So there it is, okay? What is the utility here? Well, now we took a generated carbonyl, right, and we were able to add more carbons to it. We formed carbon-carbon bonds. Very powerful. What's the downside of this? Well, the downside is we had to use an extremely powerful base to do this. And if we had any kind of protic functional group there, right, or even if we had somewhat acidic hydrogens bound to carbons, right, this would go after, right, this not organolithium, the Grignard would go after those acidic hydrogens, and it would prefer to do the acid-base reaction rather than, rather than the nucleophilic attack here. And in fact, it probably still would in this case. We'll talk about we'll talk about 1,2 and 1,4 additions and these kind of reactions with carbonyls just a little bit later, right? And we'll need powerful bases to do that also. But anyway, the majority of the reaction, or the dominant reaction, the major product is going to be this attack here, right? But that's useful, right? We started out with a carbonyl, a ketone, and we ended up with a tertiary alcohol at the end. And then, there's a lot of reactivity we can do with an alcohol. We can turn it into a halide. We can eliminate it. We can, do whatever we need to do with it, okay? But that's pretty useful for us. The downside being, right, obviously, that we have to have a powerful base. This will work with aldehydes also. Are you guys ready? We're gonna do the exact same thing, but with an aldehyde. Fantastic, right? Now, did you guys stop and think about something? I think I did, right? Remember, one thing to pay attention to is whether we're under acidic or basic conditions. That's going to determine kind of the first step in the mechanism, whether we attack the carbon or the oxygen with the carbonyl. The second thing to pay attention to is whenever we open the door, we always need to say, can I close the door? Closing the door would involve the presence of a good leaving group. Now, I know, so far we have really not seen any reactions where we can come back in and close the door, okay? But now that we're starting to get to towards the end of chapter 19, and as we start to progress towards the other chapters, we're going to see this repeated type of reaction happen. Open the door, close the door, open the door, close the door, okay? So start to get into the habit of developing those two questions. Acid or base, right? And can I close the door by having a good leaving group? Now, is hydrogen a good leaving group? No, okay? In the previous example, was carbon a good leaving group? No, right? So we don't have to worry about closing the door again, right? We just have attack at the carbonyl carbon. But, like I said, let's see if we can overcome some of the negatives of this by being able to use a carbonyl group to add carbon-carbon bonds without having these extremely powerful basic conditions, okay? And so what we want to do is something called a Wittig, all right? And this is, again, one of those quintessential organic chemistry lab reactions, right? Now, first of all, we have to make, there's basically two components to a Wittig. We have to make the Wittig reagent, and then we have to react that Wittig reagent with the carbonyl compound, okay? And those are two separate things. So whenever I'll go, look, okay? I'm gonna give you guys a hint, right? On the next exam, I'm going to ask you guys, and you're going to have to be able to use a Wittig reagent, okay? I know you're shocked that something that's has its own section in a chapter is going to show up on an exam. I can tell that you guys are amazed by my revelation to you guys. But whenever you generate a Wittig, you have to do two separate steps. You have to generate the Wittig reagent, and then you react it with the carbonyl. You can't do it all at once, and I'll talk about why in just a second, okay? So let's talk about what a Wittig reagent is. Here's the basic components of it. A Wittig reagent, I'm going to have to do a little bit of drawing here. So we've got a phosphine. So we've got our buddy triphenylphosphine. Now triphenylphosphine is just one of these. Every organic lab, right? Every chemistry lab, if you walk into it, they're going to have a bottle of triphenylphosphine, right? It is just one of these extremely common reagents that's used in a lot of different places. It's used to generate Wittigs, which are very powerful reactions for organic synthesis. It's used in organometallics and inorganic chemistry. Triphenylphosphine is a really, really useful ligand. I believe, still in the current generation Monsanto catalyst where they generate acetic acid, they still have triphenylphosphines there. It's cheap, it's easy to use, it's easy to separate, it's easy to identify. It is just a very useful reagent for us. So we end up seeing triphenylphosphine in a lot of different places. Here, it's going to help us to make the Wittig reagent. What we have to do is take triphenylphosphine and we react it with a typically a primary alkyl halide, okay? So let's give it a primary alkyl halide. I am partial to my buddy butyl bromide. That's just because of the research that we do, but that's a different argument for a different day. And I will mix these two together. Easy reaction. Nice, solid, this is an easy to measure out liquid. You mix them together, you just heat it up. You go have a cup of coffee. By the time you get back from it, this reaction is typically done, right? All you have to do is heat it up. There's not much you have to do to even clean it up. What happens then, let's do this. All right, we'll just abbreviate the benzene rings as pH phenols, right? Okay. What reaction happened? Can you guys draw the mechanism for this? You better, right? So phosphorus has a lone pair on it, right, which makes it a very good nucleophile. This is why it can, as I mentioned, right, it's useful in a lot of different places, right? It's a good ligand for metals, especially for softer metals, right? We've got a primary alkyl halide. It's got a good leaving group. This is setting up conditions for an SN2, right? Now, typically, right, we don't deal too much with SN2s that yield salts, but this is a nice tetrasubstituted phosphonium compound. And we've got our halide salt there. This is a nice white powder. You can recrystallize it, make it as pure as you can, grows these massive chunky crystals, which are very, very, very beautiful to look at, right? But anyway, so we make this. We're still not quite done yet, okay? So we take this salt here, we take this phosphonium salt, okay? And then we add in one of the other most common reagents that's found in every lab, and that's N-butyl lithium, right? N-butyl lithium. And when we add in N-butyl lithium, then what happens is we make this. Okay? So lithium bromide will precipitate out of this reaction. This is typically in a solution of pentane, or is what it is, right? And we run this in THF, and so lithium bromide is going to precipitate out, which kind of drives this reaction, these kind of things. Butane will bubble out of this reaction, all this kind of stuff. What is N-butyl lithium? N-butyl lithium is a powerful base, right? It's an organolithium compound. It's going to go after this acidic hydrogen right there, which sets up this Zwitter ion here, right? This internal salt, if you kind of want to think about that, right? We've got a plus next to a minus. Ooh, that's unusual, right? What we call this is what we call an ylide, Y-L-I-D-E, right? The ylide. Okay. This is our Wittig reagent, okay? This is our Wittig reagent. So this is what we have to do first. So if we were in the lab trying to do this, we would run through these two steps, right? We would do the alkylation followed by the N-butyl lithium, right? And so in the book, they kind of combine these together, right? So let's just draw that out just for argument's sake to kind of see what happens. Typically, you would see something like this. What color did I use? Black, right? I just forgot about it. Yep. So oh my gosh, PPH3, right? So typically you'll see it abbreviated this, triphenylphosphine, right? And I used green, okay? So let's do this then, right? So triphenylphosphine, Step 1, you would say what alkyl halide you want to use, and then step 2, you would say that you came in, right? You would came in and generated the Illid salt there. And my product would be exactly what we drew up there, right? It is this. Fantastic. Okay, so this is how we generate the Wittig reagent, right? When I talk about the Wittig reagent, I'm basically saying the Illid there. Either way is fine, right? I don't really care which one you guys want to say. What's one of the most important things you guys can ever look for in organic chemistry? Well, is where are the negatives and where are the positives? Well, it's very easy in a Wittig reagent because it's right there, right? The negative and the positive, okay? Now, we have to think here for just a second, okay? We have to think here for just a second. What do formal charges tell us, right? Formal charges are hey, pay attention, there's something odd going on, okay? A positive charge on a phosphorus, that tells us that it's deficient of electrons in the sense of, not that it lost electrons, but its electrons are being donated out to things, right? So there are no lone pairs on that phosphorus, okay? What does a negative charge on a carbon mean? A negative charge on a carbon tells us there is a lone pair on there, and that's going to be important. So despite having a negative and a positive together, we can't bring those two together to make a pi bond, right? We might expect that maybe, we could draw some kind of resonance structure in there, although phosphorus doesn't have an open orbital for us to do that, right? You'll just have to take my word for that now. When you guys go on to inorganic chemistry, then you guys will learn why that is the case, right? So you guys will be able to explain why and be able to draw the molecules and all the kind of stuff that go, excuse me, not the molecules, the orbitals that go with that, okay? So, but for the moment, understand that really what we're seeing here is a lone pair on that carbon, okay? That's going to be important. Because whenever you see a lone pair on that carbon, that's negative and that's going to go after something that's positive. So if we take our Illid there, right, our Wittig reagent, and we put it in the presence, let's use purple again, okay? So if we put it in the presence of I want to draw that a little bit bigger. You guys will see why here. Let me draw it exaggeratedly huge, okay? So if I take these, right? If I take my Wittig reagent and I react it with an aldehyde or a ketone, if I take my Wittig or the Illid and I react it with an aldehyde or a ketone, magic's going to happen. It's not really magic, right? It's science, but same idea, okay? Here's what's going to happen. The negative is going to attack the positive. You guys shocked yet? You shouldn't be, right? So we attack here, right? At the same time, let's do red. Red should be fine, right? Watch this for just a second, okay? At the same time, if we attack the carbonyl-carbon, we have to open the door, right? So I could draw a series of arrows wherein I open the door and the lone pair from the oxygen attacks the phosphorus, okay? Now you can combine those two together, right? We could just draw an arrow from here to attack the phosphorus. That would be just fine. That's the same net result. But this happens all at once. Negative attacks the carbonyl, negative of the oxygen then attacks the positive here, right? So two negatives attack two positives. Now this is kind of unusual because it's going to generate an odd looking intermediate. So give me just a second here to draw this. Okay. I'm trying to follow all the coloring, right? So red to phosphorus, right? We have our phenyl rings around, right? This was a green here, and we did purple, right? Purple to the carbonyl carbon there, and then we got the rest of the alkyl chain there, okay? Good? So take a pause and draw this out if you guys need to, or just follow the arrows over there. So we make this kind of square intermediate, okay? And then we kind of collapse these together here. All right, so let's do this. We're going to do that arrow, okay? And we're going to do that arrow. And what we effectively end up trading is we're going to end up trading a phosphorus carbon bond, right, for a phosphorus oxygen double bond. Now, phosphorus and oxygen, very, very, very good friends. They make strong, strong, strong bonds, okay? And, well, I'm going to skip that story. Probably not appropriate for a, anyway, it's fine. So phosphorus and oxygen, what we need to, the phosphorus has been used in perhaps nefarious applications is where I'll leave it for that story there, okay? But anyway, so what we'll end up trading here, right, is a weaker bond for a stronger bond. Phosphorus for oxygen, double bond, very, very strong, right? We're gonna have trading that for a phosphorus to a carbon bond there, okay? So let's draw the product of this. I'm going to give myself some space, so just duplicate this and bring it down. And let's see what ends up here, right? So purple, 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 we made a red bond here to, right? Let me put a black dot on that carbon right there, okay? Guys with me? And then the other product that we end up making out of this is, there's my phosphorus. That was red, and then this was purple. Okay. Triphenyl phosphine oxide, right? Also a pretty useful reagent for some cases, but an easy product to separate in this case, right? Do you guys catch this? So that is the mechanism for this reaction. So you guys learn the mechanism for this. I specifically show this one, even though it's very unique, right? And I kind of make a promise to my students that I won't show them mechanisms or make them, excuse me, not that I won't show them mechanisms, that I won't make them memorize mechanisms that are really only applicable to one thing. But this is such a useful reaction, and actually an extremely, as you get later on in your career, an extremely common set of bond breaking and bond forming, especially in organometallics. Having these kind of square intermediates and this kind of stuff, you'll see this again and again, right? So depending on where you go with your chemistry career, you actually will see this mechanism in its bits and pieces show up again, right? We have attack from the negative to the carbonyl, the oxygen attacks the phosphorus, generate the square intermediate, right? We trade bonds and we end up with this product here. So let's clean this up just a bit and show you guys what the net result is. So the net result is this. We started with a carbonyl, just to keep things simple, right? I'm going to skip the other stuff in between there and say my final product was this. Okay? What did I end up doing? Essentially, I ended up taking my alkyl halide and putting it in place of the oxygen. That's it. Extremely useful, okay? Things to pay attention to. How many carbons you have in that chain that you add. We start out with 4, make sure you add 4. 1, 2, 3, 4, okay? That one right there is the one that always gets forgotten, right? We tend to drop or add one by accident, right? So if you, what you put in is what you get out. Garbage in, garbage out, right? 4 carbons in, 4 carbons out. But this is our Wittig. Okay, so an easy way, a mild way, and a selective way of making carbon-carbon bonds. Okay, very, 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 very useful. Okay, and I think I've said this a million times and I'll be done with it. Now, let me talk one more thing, right? And this will be a good practice for you guys. I want you guys to make that. Okay? Now this is basically the opposite almost of a previous example that we did. Okay? I want you guys to make this here. You can do it essentially in 2 steps. Okay? So take a minute, see if you guys can run through this. Another good time for me to grab a drink here, right? Wonderful. All right. So what we will do, first things first, we identify a carbonyl, and we notice that with that carbonyl, all I did was swap it out for a carbon, okay? So what I'm going to do is I'm going to make a Grignard. Excuse me, I'm going to make a Wittig, not a Grignard. What I'm going to do is add methyl iodide or methyl bromide, doesn't really matter, right? I would use methyl iodide because that's actually a liquid and it's in the lab and it's easy to use. Methyl bromide is technically a gas. Well, not technically, it is a gas, right? So it's a little bit harder to use, but it doesn't really matter. We're doing chemistry on paper, right? Every time I try and set up a Wittig, I better bring in my base to make the illid salt. And so my product here would be okay. Here's my illid salt. Take my illid into my carbonyl here. So illid, and that's it. So really only 2 steps, right? Make the illid, add the illid. Wow, that's not too bad. Here's where your practice comes in. Try and do this without a Wittig. Do you guys see the challenge? The challenge is I made a terminal, right? A terminal alkene. That's not that easy to do, right? I made a terminal alkene while adding a carbon to it. So there's your challenge. Do this without a Wittig. It's going to take you 1, 2, 3 steps, maybe 3 or 4 steps, depending. There's multiple ways to do it, right? So see if you guys can come up with this in a different way without using an illid, and what are the pros and cons of using the illid versus the other methods that you guys came up with, okay? You can do it, right? You can do it other ways, but you know, let's see what the different ways are and what the pros and cons are. Remember, those are the types of questions I'd like to ask you guys, right? Why would I prefer to do this synthetic route versus another one? What's the benefits of this? Why did you choose these reagents? That kind of stuff, okay? But there it is. So I think that's kind of the main thing that I want to talk to you guys about in this video. I didn't get quite as far as I thought I would, but that's okay too, right? We got plenty far enough. We learned about adding hydrogens. We had our reductions with LAH and sodium borohydride. We talked about Grignards and how they react with our carbonyls, and then we talked about our new useful Wittig reagents, okay? Essentially, that's the end of chapter 19, right? The page 887, right, page 887. One thing I do like about this book is that they put a fantastic set of review pages at the end of each chapter, right? So 887 gives you a list of 15 different reactions, right? 15 different reactions that come out of this chapter. So pay attention to that, take a look at that, right? And then make sure that you guys kind of spend the time working through the practice problems that you guys have. Next time, we will move into chapter 20, right? We'll talk about carboxylic acids, right? Okay, so I will see you guys next time then.